Welcome students to the fourth lecture on operational amplifiers. Myself, Dr. Kirti Vyas from Arya College of Engineering IT. In the earlier lecture, we have discussed about some introductory parameters of operational amplifiers. Today, we are going to start with gain bandwidth product. The gain bandwidth product is the bandwidth of the op-amp when an open loop voltage gain is reduced to 1. Here in this particular diagram you can see gain versus frequency plot has been drawn, and you can see at 10 megahertz the mid voltage gain is very high, and after that particular 10 hertz value it is decreasing and it can be found till 1 megahertz. This particular graph is corresponding to 741 op-amp. So this particular open loop gain versus frequency characteristic is quite important in realizing certain circuits where you want the amplifier to work efficiently as in your particular chosen frequency ranges. Next, we move on to slew rate. Slew rate is also very important parameter. It is defined as maximum rate of change of output voltage per unit of time under large signal conditions. It is expressed in volts per microsecond. What this particular sentence is saying, that whenever you are applying large signal, that is signals which are having large amplitude excursion, then the slew rate is rate of change of output with respect to input with respect to the time. The slew rate indicates how rapidly the output of an op-amp can change in response to change in the input frequency with input amplitude constant. The slew rate changes with change in voltage gain and is normally specified at unity gain. If the slope requirement is greater than the slew rate, then your distortion are going to occur inside the circuit. For 741C, which we have already discussed in our lecture, the slew rate is low, 0.5 volt per microsecond, which limits is used in high frequency application. That is, for high frequency application you need to have certain op-amp which are upgraded as compared to 741C. Now we will take one particular example to find out the slew rate when the capacitor value inside a particular circuit and maximum charging current values are given. For a slew rate, since it is dV by dt, obviously it is I by C value. Substituting the value of I and C, we find that slew rate is 1.5 volt per microsecond. Next, again we have one more example. The operational amplifier has a slew rate of 2 volt per microsecond. The output is also given as 12 volt. What is power bandwidth? Since we know that slew rate is equals to 2 pi FVP, so we are able to find out the F max, which comes out to be 26.5 kilohertz. So the bandwidth becomes 26.5 kilohertz. Now we discuss about the equivalent circuit of an op-amp, which is shown in figure 2. Here V1 and V2 are the two input voltages. R1 at the input port is the input impedance of the op-amp. AD into VD is equivalent Thevenin voltage source. RO is the Thevenin equivalent impedance looking back into the terminal of the op-amp, and plus VCC minus VE are the power supply connected to the op-amp. Now, what is utility of this particular equivalent circuit? This equivalent circuit is useful in analyzing the basic operating principle of op-amp and in observing the effect of standard feedback arrangement. And output of this op-amp will be equal to the differential gain AD into difference of input applied, that is V1 minus V2. This V output can also be written as AD into VD. The polarity of the output voltage will depend on the polarity of the difference voltage VD. Now, another important aspect of op-amp is ideal voltage transfer curve. As you can see, this is a graphical representation of output equation which was shown in figure 3, that is V output equals to AD into V1 minus V2. Here we can see that output voltage VO is plotted against the differential input VD, keeping AD constant. What we observe from this ideal voltage transfer curve is that the output voltage cannot exceed the positive and negative saturation voltages. These saturation voltages are specified for a given value of supply voltages. This means that the output voltage is directly proportional to the input difference voltage only until it reaches the saturation voltage and thereafter the output voltage. So this is how the op-amp is going to respond to your applied difference input. This curve is also known as ideal voltage transfer curve. It is known ideal because the output offset voltage is assumed to be 0. If the curve is drawn to scale, the curve would be almost vertical because of very large value of AD. So this will help us in designing many circuits out of our op-amp. Now we will talk about some open loop op-amp configuration. First of all, what do you mean by open loop? The open loop indicates that no connection exists between the input and output terminal of op-amp. That is, the output signal is not feedback in any form as a part of the input signal. In open loop configuration, the op-amp functions at a high gain amplifier. Now we will see that there are three important open loop configuration. First one is already talked of in many of the lectures, is differential amplifier. Here you can see two input signal V in 1 and V in 2 are applied correspondingly to the non-inverting and inverting terminal of the op-amp, and the output is equals to V01 minus V input 1 minus V input 2. So the op-amp is amplifying the difference between two input signal, so it is also known as differential amplifier in this case. The source resistance value Ri1 and Ri2 are normally negligible compared to the input resistance Ri. So we are assuming that almost negligible voltage drop occurs across this resistance value. So V1 is equals to VIN1 and V2 is VIN2. That is why it is written at the output that the output is almost equals to Vin minus Vin2. Here AD is the open loop gain. Now the inverting amplifier. The inverting amplifier means that the input is applied only to the inverting terminal and non-inverting terminal is grounded. The configuration is shown in the figure 5, that is V1 is 0 and V2 is Vin. So, according to the equation given on the top of the slide, the V output becomes V minus AD Vin. So, a minus sign occurs. That means whatever input was applied has been inverted and there is a phase difference of 180 degree from the output to the input. The output and input differ in 180 degree phase. The non-inverting amplifier. I hope you have already understood the inverting amplifier. The non-inverting amplifier is about applying input to the non-inverting terminal, and obviously the V1 will be plus Vin, V2 is 0 and V output is plus AD Vin. This means that the input voltage is amplified by AD and there is no phase reversal at the output. This is the diagram of a non-inverting amplifier where input is applied to a non-inverting terminal, inverting terminal is connected to ground and V output equals to AD times of Vin. When operated in open loop, the output of the op-amp is either negative or positive saturation or switches between positive and negative saturation level. Therefore, the open loop op-amp is not used in linear applications. Thank you for listening to this lecture. In next series, we will talk about more of op-amp and we will talk about closed loop configuration of op-amp.